Right now, you are standing on a speck of rock 8,000 miles wide. Sounds big until you learn the sun could swallow 1,300,000 of those rocks. Sounds enormous until you learn our sun is one ordinary star among 400 billion others in a single galaxy. Sounds incomprehensible until you discover that the galaxy is one grain of sand in a cosmic ocean containing 2 trillion other grains, each packed with hundreds of billions of its own stars. And all of that, every galaxy humanity has ever photographed or imagined, fits inside a visible bubble that might represent less than 1% of what actually exists. The true scale of the universe does not just surprise you, it demolishes every intuition your brain has ever built. If you enjoy having your sense of reality completely rebuilt from the ground up, go ahead and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives for you. Now, let's begin. Start with your body. You are roughly 6 feet tall. That height is the baseline your brain uses to interpret every distance you will ever encounter. The hallway to your kitchen, the walk to the corner store, the drive across town. All of these measurements are processed by a brain that evolved to navigate distances a human being can walk in a single day. Your ancestors needed to judge the distance to a water source, the length of a hunting trail, the width of a river crossing. Evolution built your spatial intuition for a world measured in footsteps, and that intuition is about to become worthless. The tallest building on Earth, the Burj Khalifa in Dubai, stands 2,717 feet, impressive by human standards. You could stack roughly 450 people head to toe to match its height. Standing at its base and looking up, your neck cranes and your sense of proportion already starts to wobble. But the Burj Khalifa is a splinter. Mount Everest rises to 29,032 feet above sea level. Stack 10 Burj Khalifas on top of each other and you still fall short of the summit. Climbers who reach that peak describe a sensation of standing on the edge of Earth itself. The sky above turns a deep indigo. The curvature of the planet becomes faintly visible. Yet this mountain that has killed hundreds of people and broken the bodies of thousands more barely qualifies as a surface blemish on the planet it sits on. Earth measures just under 8,000 miles in diameter. If you could drive a car straight through the planet from one side to the other at highway speed, the trip would take about 5 days. The circumference at the equator stretches approximately 24,900 miles. A commercial airliner traveling at 550 miles per hour would need just over 45 hours to circle the entire globe without stopping. That number feels manageable. 2 days in a plane and you have wrapped around an entire world. Your brain can almost hold that distance. It strains, but it holds. Now, leave the surface. The International Space Station orbits Earth at an altitude of roughly 250 miles. Astronauts aboard the station complete one full orbit every 90 minutes, racing around the planet at 17,500 miles per hour. From that vantage point, Earth fills most of the view. Continents drift past below. Hurricanes spiral in white pinwheels over blue oceans. The planet looks enormous and alive. But the station floats barely above the atmosphere, skimming along the outermost edge of Earth's gaseous envelope. If Earth were a basketball, the space station would orbit less than 1/4 of an inch above its surface. You would need a magnifying glass to see the gap. That is how close humanity's permanent presence in space actually is to the ground. The moon changes everything. Earth's nearest celestial neighbour orbits at an average distance of 238,900 miles. To appreciate that number, imagine lining up 30 Earths side by side, shoulder to shoulder like a row of planets. The moon sits at the far end of that line. When the Apollo astronauts left Earth orbit and aimed for the moon, the journey took roughly 3 days. 3 days of coasting through absolute emptiness with Earth shrinking behind them, and a grey, cratered world growing slowly in the forward window. During those 3 days, the astronauts travelled farther from home than any human being had ever gone, Radio signals between mission control and the spacecraft experienced a delay of about 1 1/3 seconds. Light itself needs that long to cross the gap between Earth and the Moon. That 1 1/3 second delay is the first crack in your intuition. You make a phone call and expect an instant response. Conversations flow without noticeable lag. But at the Moon's distance, the speed of light already introduces a pause you can feel. Ask a question, wait 1 1/3 seconds for it to arrive, wait another 1 1/3 seconds for the reply to come back. A nearly 3-second round trip, annoying during a phone call. Manageable. But this is only the Moon, the nearest object of any significance to Earth. The first rung on a ladder that stretches so far upward you cannot see where it ends. The Sun sits approximately 93 million miles from Earth. Astronomers call this distance 1 astronomical unit, and it serves as the standard yardstick for measuring everything within the solar system. 93 million miles. If you could drive a car to the Sun at 60 miles per hour without stopping for fuel, food, or sleep, the trip would take roughly 177 years. You would need to start driving before the American Civil War, and you still would not have arrived yet. A commercial jet would need about 19 years of continuous flight. Even light, the fastest thing in the universe, needs 8 minutes and 20 seconds to cover the distance. Every time you look at the Sun, you are seeing it as it appeared 8 minutes ago. If the Sun vanished this instant, you would continue to see its light and feel its warmth for another 8 minutes before darkness arrived. The Sun itself is staggering. Its diameter stretches 864,000 miles. You could line up 109 Earths across its face. Its volume could contain approximately 1,300,000 Earths. It accounts for 99.86% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, every grain of dust orbiting our star adds up to barely a rounding error compared to the Sun itself. Jupiter, the largest planet, a gas giant so massive it could swallow all the other planets combined, is still roughly 1,000 times less massive than the Sun. Earth is a moat circling a furnace, and that furnace dominates everything within its gravitational reach. But the Sun's gravitational reach extends far beyond the familiar planets, and this is where earthly intuition begins to collapse entirely. Mars orbits the Sun at an average distance of 142 million miles, roughly 1.5 astronomical units. When Mars and Earth are on the same side of the Sun at their closest approach, the gap between them shrinks to about 34 million miles. Even at that minimum distance, a radio signal travelling at the speed of light takes over 3 minutes to cross the void. Conversations become impossible. Mission controllers sending commands to a rover on Mars must wait between 6 and 44 minutes for a round-trip response depending on orbital positions. The rover operates largely on its own, making decisions autonomously, because real-time guidance from Earth is physically impossible. The distance has made the speed of light feel slow. Jupiter orbits at 5.2 astronomical units from the Sun, approximately 484 million miles. Saturn sits at 9.5 astronomical units. These outer planets exist in a realm of cold and darkness where sunlight has grown feeble. At Saturn's distance, sunlight is roughly 100 times dimmer than it appears from Earth. A human standing on one of Saturn's moons would see the Sun as a bright star rather than the blazing disk we know. Radio signals from the Cassini spacecraft orbiting Saturn took between 67 and 85 minutes to reach Earth. Data from those distant observations arrived on scientists' screens more than an hour after the spacecraft recorded them. By the time an image of Saturn's rings appeared on a monitor in Pasadena, the spacecraft had already moved thousands of miles from where it took the picture. Uranus orbits at roughly 19 astronomical units. Neptune, the outermost recognized planet, sits at approximately 30 astronomical units from the Sun. At Neptune's distance, the Sun has shrunk to a point of brilliant light, barely distinguishable from a very bright star. Light from the Sun takes over 4 hours to reach Neptune. A spacecraft travelling from Earth to Neptune, as Voyager 2 did, required 12 years to make the journey. 12 years of flight through mostly empty space, past gas giants and their moons, through radiation belts and magnetic fields, deeper and deeper into a solar system that kept revealing how much farther it extended than anyone intuitively expected. The Voyager missions rewrote humanity's sense of cosmic proportion. Voyager 1 launched in September 1977. As of early 2026, it has been travelling for over 48 years and has reached a distance of approximately 165 astronomical units from the Sun. That translates to more than 15 billion miles. Voyager 1 is the most distant human-made object in existence. It crossed the boundary of the heliosphere, the bubble of charged particles the Sun blows outward into space, in August 2012, becoming the first human artifact to enter interstellar space. 15 billion miles sounds like the edge of everything. It is not even close to the edge of anything. The Oort cloud marks the true outer boundary of the Sun's gravitational dominion. This theoretical shell of icy bodies is believed to surround the solar system in a roughly spherical halo, extending from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. 100,000 astronomical units. That is approximately 1.6 light years. The Oort cloud is so distant that objects within it take millions of years to complete a single orbit around the Sun. Comets that fall inward from this remote reservoir and streak past Earth on long elliptical paths may not return for tens of thousands or even millions of years. At Voyager 1's current speed of roughly 38,000 miles per hour, the spacecraft would need about 500 years to reach the inner edge of the Oort cloud. It would require approximately 30,000 years to pass through the cloud entirely and emerge on the other side. 30,000 years. Human civilization as we know it is roughly 10,000 years old. Voyager would need 3 times the entire span of recorded human history just to cross one structure within our own solar system. And yet, at 1.6 light years across, the Oort cloud represents only a fraction of the distance to the nearest star. The closest stellar neighbour to our Sun is Proxima Centauri, a dim red dwarf sitting 4.24 light years away. That means light itself, racing at 670 million miles per hour, needs over 4 years to travel from here to there. Voyager 1, our fastest emissary, travelling at its current velocity, would need roughly 73,000 years to reach Proxima Centauri if it were heading in that direction. 73,000 years. The last ice age ended about 11,700 years ago. Voyager would need to fly for more than 6 ice ages laid end to end before it reached the nearest star. Consider what that distance means in physical terms. If you shrank the Sun down to the size of a golf ball and placed it on a table in front of you, Earth would be a grain of fine sand orbiting about 15 feet away. Jupiter would be a small pea circling at roughly 77 feet. Neptune, a slightly smaller pea, would orbit at 450 feet. The Oort cloud would extend outward for roughly 300 miles in every direction, a gravitational territory the size of a small state surrounding one golf ball. And Proxima Centauri, the nearest neighbouring golf ball, would sit approximately 750 miles away. 750 miles of absolute emptiness between 2 tiny spheres. That is the interstellar neighbourhood. That is how far apart stars actually are. This emptiness defines the solar system's true character. The planets feel like a crowded family when you see them drawn in textbook diagrams, neatly spaced along colourful orbital lines. Those diagrams are lies. They compress distances by factors of thousands to fit on a page. In reality, the solar system is almost entirely vacuum. If you threw a dart randomly into the volume of space enclosed by Neptune's orbit, the odds of hitting anything, any planet, any moon, any asteroid, are so microscopically small they are effectively zero. Space is empty. Profoundly, relentlessly, overwhelmingly empty. The objects within it are specks scattered across a void so vast that calling it big misrepresents it entirely. The New Horizons spacecraft, which flew past Pluto in July 2015, provided a visceral demonstration of this emptiness. After its encounter with Pluto at roughly 33 astronomical units from the Sun, New Horizons continued outward into the Kuiper Belt, the region of icy bodies beyond Neptune. In January 2019, it flew past Arrokoth, a small contact binary object at approximately 44 astronomical units. Beyond Arrokoth, New Horizons continues to fly through increasingly empty space. Its instruments detect the faintest whispers of solar wind particles and cosmic dust grains. The environment is as close to perfect nothingness as nature allows. Temperatures hover just a few tens of degrees above absolute zero. Sunlight has faded to a pale dot barely brighter than the surrounding stars. The spacecraft is utterly alone, surrounded by trillions of cubic miles of nothing. This loneliness has a quantitative dimension that is worth pausing on. The average density of matter within the solar system, if you spread all the mass of every planet, moon, asteroid, and comet evenly across the volume enclosed by the Oort cloud, works out to something vanishingly close to a perfect vacuum. The Sun holds virtually all the mass, and it occupies a laughably tiny fraction of the total volume. Everything else is space. Not metaphorical space. Actual, physical, three-dimensional emptiness extending in every direction for billions of miles. This is the solar system. This is everything humanity has ever physically explored, touched, or sent a machine to visit. Every Apollo mission, every Mars rover, every flyby of Jupiter and Saturn and Pluto, all of it has occurred within this single star's gravitational territory. Not one human-made object has reached another star. Not one signal we have sent has had time to travel to even the closest stellar neighbour and return. We are confined to a single tiny island in an ocean so vast that the nearest neighbouring island requires a journey measured in tens of thousands of years at our fastest current speed. And here is the detail that collapses the first layer of intuition entirely. The solar system, from the Sun out to the edge of the Oort cloud, spans roughly 3 light-years in diameter. The Milky Way galaxy, in which the solar system resides, stretches roughly 100,000 to 200,000 light-years across depending on how you measure it. That means the galaxy is at minimum 30,000 times wider than our entire solar system. Everything we have explored, every planet we have photographed, every comet we have tracked, every void we have crossed, fits inside a structure that is at least 30,000 times larger. If the solar system were a single grain of salt, the Milky Way would stretch across a full-size basketball court and beyond. We have not even begun to talk about what lies beyond the galaxy. The solar system is the smallest unit of measurement on the scale we are about to climb. Every distance you just struggle to comprehend, the 93 million miles to the Sun, the billions of miles to Neptune, the trillions of miles to the Oort cloud, all of it collapses into a single invisible point when viewed from the next level up. The numbers are about to get so much larger that the distances within our solar system will stop registering entirely. They will round to zero, not approximately zero, functionally, meaningfully, definitively zero. Voyager 1 has been flying for nearly half a century. It has travelled farther than any object humanity has ever built. It carries a golden record with sounds and images from Earth, a message in a bottle tossed into a cosmic ocean, and after 48 years of relentless travel at 38,000 miles per hour, it has crossed less than 0.1% of the distance to the nearest star. That is where we are. That is how far we have gone. That is the sum total of human physical reach into the cosmos, a fraction so small it vanishes when you round to the first decimal place. The next step takes us across a gulf that makes the entire solar system disappear. The gap between our solar system and the nearest star is not a distance your brain was built to process. 4.24 light-years to Proxima Centauri. Those words slide past without friction because they sound like a simple measurement. A number followed by a unit. But that unit, the light year, is doing all the heavy lifting, and your mind is letting it pass unchallenged. 1 light year equals approximately 5.88 trillion miles. Multiply that by 4.24, and the distance to Proxima Centauri reaches roughly 25 trillion miles. Written out in full, that number stretches long enough to make your eyes glaze. 25 followed by 12 zeros, and this is the closest star, the absolute nearest pinprick of nuclear fire in our stellar neighborhood. Everything else is farther. The interstellar medium between here and there is not the same vacuum you find between planets. It is emptier. Within the solar system, the sun's solar wind fills space with charged particles, a tenuous plasma that thins with distance but never entirely disappears until you reach the heliopause. Beyond that boundary, interstellar space contains roughly 1 atom per cubic centimeter. For comparison, the air you are breathing right now holds approximately 25 quintillion molecules per cubic centimeter. The difference between those two numbers is so extreme that interstellar space qualifies as a better vacuum than anything ever produced in a laboratory on Earth. If you stood unprotected in that void, you would not be surrounded by darkness, you would be surrounded by nothing. The space between stars is the closest thing to true emptiness that exists in nature. Yet this emptiness is not featureless. Vast clouds of molecular hydrogen drift between the stars, some of them stretching dozens of light years across. These molecular clouds are stellar nurseries, regions where gas slowly accumulates under its own gravity until pockets of it collapse, heat up, and ignite nuclear fusion. Every star you have ever seen in the night sky was born inside one of these clouds. The Sun itself formed roughly 4.6 billion years ago from a collapsing region within a molecular cloud that no longer exists. The material that became Earth, that became you, was once scattered through interstellar space as atoms of hydrogen, helium, carbon, oxygen, and iron drifting in the void between older stars that had already lived and died. This is one of those facts that sounds poetic but is physically literal. The iron in your blood was forged in the core of a massive star that exploded as a supernova billions of years before the solar system formed. The calcium in your bones was produced by a different type of stellar explosion. The oxygen you breathe was fused in the furnace of yet another star. You are not metaphorically made of stardust. You are materially, chemically, atomically constructed from elements that were manufactured inside stars and ejected into interstellar space through violent deaths. The void between stars is not just empty distance, it is the medium through which the raw ingredients of planets and people were transported across light years and billions of years of cosmic time. But not all of those 400 billion stars are built alike, and the diversity hidden within that population is staggering. The Sun is a yellow dwarf, a middle-aged, medium-temperature, medium-brightness star that will burn steadily for roughly 10 billion years before swelling into a red giant and eventually collapsing into a white dwarf the size of Earth. It is the most ordinary kind of star imaginable, cosmically unremarkable, and it represents only one narrow category among many. Red dwarfs are the most common stars in the Milky Way, accounting for roughly 70 to 75% of the entire stellar population. They are small, dim, and cool compared to the Sun, with surface temperatures ranging from roughly 3,000 to 4,000 degrees Kelvin. The smallest red dwarfs contain only 8% of the Sun's mass, barely enough to sustain hydrogen fusion in their cores. What they lack in brilliance, they compensate for in longevity. A red dwarf burns its fuel so slowly that it can shine for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not one has yet had time to die. These dim, patient stars are the most numerous objects in the galaxy, yet almost none of them are visible to the naked eye from Earth. The night sky you see is dominated by rare, luminous giants. The true population of the galaxy hides in the dark. At the opposite extreme sit the blue supergiants, stars so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can contain 50 or even 100 times the mass of the Sun, with surface temperatures exceeding 30,000 degrees Kelvin. Their luminosity outshines the Sun by factors of hundreds of thousands. A single blue supergiant can pump out more energy per second than an entire cluster of red dwarfs produces in a year, but their ferocity is their undoing. These stars live fast, fusing heavier and heavier elements in their cores until they reach iron, at which point nuclear fusion can no longer sustain them against gravitational collapse. The core implodes. The outer layers are blown outward in a supernova explosion that can briefly outshine the entire galaxy. What remains depends on the mass. Some leave behind neutron stars, objects so dense that a teaspoon of their material would weigh roughly 6 billion tons on Earth's surface. The most massive leave behind black holes, regions of space-time where gravity is won so completely that nothing, not even light, can escape. Neutron stars are among the most extreme objects in the galaxy. They pack roughly 1.5 times the mass of the Sun into a sphere only 12 miles across. Their density exceeds 100 trillion times the density of water. Their surfaces are coated in a crystalline lattice of iron nuclei, compressed so tightly that the material is harder than anything that exists on Earth. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like cosmic lighthouses. These are pulsars, and their signals are so precise that they rival atomic clocks in accuracy. Others possess magnetic fields 1 trillion times stronger than Earth's, powerful enough to erase the information on a credit card from a distance of roughly 100,000 kilometers, about a quarter of the way to the Moon. These magnetars occasionally release bursts of energy so intense that a single flare can compress Earth's magnetosphere from tens of thousands of light-years away. The Milky Way contains an estimated 100 million to 1 billion neutron stars, and perhaps 100 million stellar mass black holes, all remnants of massive stars that lived and died over the galaxy's 13 billion year history. These corpses drift through the galactic disk and halo, invisible except when they interact with nearby matter or reveal themselves through gravitational effects. You could pass within a few light years of a black hole and never know it was there. Between the extremes of red dwarfs and blue supergiants lies an immense spectrum of stellar types, each with its own mass, temperature, luminosity, and lifespan. Orange dwarfs slightly cooler than the Sun, white main-sequence stars slightly hotter, red giants that have exhausted their core hydrogen and swollen to hundreds of times the Sun's diameter, asymptotic giant branch stars shedding their outer layers into planetary nebulae, glowing shells of gas that expand into interstellar space and contribute to the raw material for new generations of stars. The galaxy is a recycling engine. Stars form from gas, burn for millions or billions of years, eject enriched material back into space when they die, and that material is gathered up again by gravity into the next generation. Each successive generation of stars contains a slightly higher proportion of heavy elements than the last, gradually enriching the galaxy's chemical inventory over cosmic time. This enrichment is why planets like Earth can exist. The first generation of stars, formed from the nearly pure hydrogen and helium left over from the Big Bang, could not have hosted rocky worlds because the heavy elements needed to build rock, iron, and water did not yet exist in significant quantities. It took billions of years of stellar nucleosynthesis, billions of years of supernovae and stellar winds scattering heavy elements into interstellar space, before the galaxy's chemical makeup was rich enough to produce the kind of planet that could support complex chemistry and eventually biology. Earth is a late-generation product. It exists because generations of stars lived and died before the Sun was born. And this brings us to one of the most profound revelations in modern astronomy. Planets are not rare curiosities. They are everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, detected over 2,700 confirmed exoplanets and identified thousands more candidates by monitoring the brightness of more than 150,000 stars and watching for the tiny dips in light caused by planets crossing in front of their host stars. Statistical analysis of Kepler's data led to a remarkable conclusion. On average, every star in the Milky Way hosts at least one planet. Many host multiple planets. Rocky worlds in the habitable zone, the orbital region where liquid water could persist on a planetary surface, are not one in a million oddities. They may number in the tens of billions within our galaxy alone. The James Webb Space Telescope has begun examining the atmospheres of some of these worlds, searching for chemical signatures that might indicate habitability or even biological activity. Water vapor, carbon dioxide, and methane have already been detected in the atmospheres of several exoplanets. The detection of biosignature gases, combinations of atmospheric chemicals that are difficult to explain without biological processes, remains the next great frontier. If such a detection occurs, it would confirm that the Milky Way is not just a galaxy of 400 billion stars with tens of billions of rocky planets. It would be a galaxy where life has independently arisen on more than one world. The scale of the galaxy is not merely a matter of distance and star counts. It is a measure of possibility. Each additional star is another furnace. Each furnace may warm another world. Each world is another experiment in chemistry that has been running for billions of years. 400 billion experiments scattered across 200,000 light-years of space, running for up to 13 billion years. The sheer number of trials that the galaxy has conducted in the chemistry of life is so large that the question is not whether conditions for life exist elsewhere. The question is how many times those conditions have produced a result. Now widen the view. The Sun is one star among approximately 400 billion in the Milky Way galaxy. That number is not precise because large portions of the galaxy are hidden behind dense dust clouds that block visible light, but modern infrared surveys and statistical modeling converge on an estimate between 100 billion and 400 billion stars, with most recent analyses favoring the higher end. Each of these stars has its own gravitational territory, its own potential retinue of planets and moons and comets. Some are solitary like our Sun. Others exist in binary or triple systems, 2 or 3 stars locked in gravitational embrace orbiting a common center of mass. A significant fraction, perhaps the majority, host at least one planet. 400 billion stars spread across a structure that spans somewhere between 100,000 and 200,000 light-years in diameter. The traditional textbook figure was 100,000 light-years, but research over the past decade using stellar streams and halo star surveys has pushed that estimate significantly upward. The visible disk of stars, the bright spiral structure you see in every artist's rendering, stretches roughly 100,000 light-years. But the galaxy does not end where the bright stars thin out. Faint stellar populations extend far beyond the visible disk, and the dark matter halo, the invisible gravitational scaffolding holding everything together, reaches out to at least 250,000 light-years and possibly much farther. The Milky Way's sphere of gravitational influence is substantially larger than the glowing disk most people picture when they hear the word galaxy. That disk is remarkably thin compared to its width. The stellar disk measures roughly 2,000 light-years in thickness at the Sun's position, though it flares outward at the edges and thickens near the center. The ratio of diameter to thickness makes the Milky Way proportionally flatter than a compact disk. If you scaled the galaxy down to the diameter of a dinner plate, the disk would be thinner than a sheet of paper. This extreme flatness results from the galaxy's rotation. Just as pizza dough flattens when spun, the rotating mass of the galaxy settled over billions of years into a thin plane where most stars, gas, and dust concentrate. The Sun orbits the galactic center at a distance of roughly 26,000 light-years, placing us about halfway between the core and the outer edge of the visible disk. We sit within one of the galaxy's spiral arms, specifically a structure called the Orion Arm or local spur, which branches between the larger Perseus Arm and the Sagittarius Arm. Our position is neither special nor central. It is suburban. We live in a galactic neighborhood that is neither the dense urban core nor the sparse rural outskirts, but somewhere in between, a quiet residential zone where stars are spaced a few light-years apart, and the night sky contains enough visible stars to inspire wonder without overwhelming the senses. The galactic center, by contrast, is a place of terrifying density and violence. Stars near the core are packed thousands of times more tightly than in our neighborhood. If Earth orbited a star near the galactic center, the night sky would blaze with so many bright stars that true darkness would never fall. It would be possible to make out a book using only starlight, but that beauty would come with danger. Stellar encounters would be far more frequent. Gravitational perturbations could destabilize planetary orbits, and radiation from nearby supernovae and the central black hole would bathe everything in lethal energy. At the very center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of our Sun. This object was confirmed through decades of painstaking observation. Astronomers tracked individual stars orbiting the galactic center and measured their trajectories with extraordinary precision. One star, designated S2, completes an orbit around Sagittarius A star every 16 years, reaching speeds of roughly 2.5% of the speed of light at its closest approach. The only object massive enough and compact enough to produce those orbital velocities without being visible is a black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing the glowing ring of superheated gas swirling around the black hole's shadow. The image confirmed what decades of indirect evidence had established. A monster lives at the heart of our galaxy. Despite its enormous mass, Sagittarius A star is surprisingly quiet compared to supermassive black holes in other galaxies. Some galactic centers are active, blasting jets of material thousands of light years into space and outshining all the stars in their host galaxy combined. Sagittarius A star is dormant, consuming very little material at present, but it was not always so calm. Observations of structures called Fermi bubbles, enormous lobes of high-energy gas extending above and below the galactic plane, suggest that Sagittarius A star experienced a period of intense activity several million years ago, producing outbursts that sculpted the gas distribution across tens of thousands of light years. The monster is sleeping, but it has not always slept. The galaxy rotates, but not like a solid wheel. Stars at different distances from the center orbit at different speeds in a pattern called differential rotation. The Sun travels around the galactic center at roughly 515,000 miles per hour. Even at that extraordinary velocity, one complete orbit takes approximately 230 million years. Astronomers call this period a galactic year. The last time the Sun was at its current position in its orbit, dinosaurs had not yet appeared on Earth. The time before that, the most complex life on the planet was fish. In the entire 4.6 billion year history of the solar system, the Sun has completed only about 20 galactic orbits. The galaxy operates on timescales that make geological ages feel brief. Differential rotation creates the spiral arms that give the Milky Way its characteristic appearance. These arms are not permanent structures made of the same stars. They are density waves, regions where stars and gas temporarily bunch together before moving on, similar to how cars slow down and cluster in a traffic jam, even though individual cars eventually pass through. Stars spend part of their orbit inside an arm and part between arms. The spiral pattern persists because the density wave itself rotates at a different speed than the stars, maintaining the spiral shape over billions of years even as individual stars drift through it. New stars tend to form preferentially inside the arms because the higher gas density triggers gravitational collapse. This is why spiral arms glow brighter than the spaces between them. They are laced with young, hot, luminous stars and the nebulae from which those stars recently formed. Beyond the bright disk, the galaxy possesses a vast spherical halo, populated by ancient stars, globular clusters, and enormous quantities of dark matter. Globular clusters are dense, spherical collections of hundreds of thousands to millions of stars bound together by mutual gravity. The Milky Way hosts roughly 150 known globular clusters, and many of them orbit far above and below the galactic plane, tracing paths through the halo that reveal the galaxy's total gravitational mass. These clusters are among the oldest objects in the galaxy, with ages reaching 12 to 13 billion years. They formed when the universe itself was young, before the Milky Way had fully assembled into its current structure. Stellar streams thread through the halo as well, and these ghostly rivers of stars have revolutionized our understanding of the galaxy's true extent. Stellar streams form when the Milky Way's gravity captures and tears apart smaller galaxies or globular clusters that venture too close. The captured stars stretch into long, thin trails that orbit through the halo for billions of years before fully dispersing. The Sagittarius stream is the most prominent example, wrapping around the entire galaxy multiple times like a ribbon wound around a ball. Mapping these streams reveals the gravitational field they move through, and that field extends far beyond the visible disk. Stars in the most distant known streams orbit at distances exceeding 200,000 light-years from the galactic center. Their presence proves that the Milky Way's gravitational influence, and therefore its true physical extent, reaches at least that far. Dark matter makes this possible. Roughly 85% of the Milky Way's total mass consists of dark matter, a substance that does not emit, absorb, or interact with light in any detectable way. Its presence is inferred entirely through gravitational effects. Stars in the outer galaxy orbit faster than they should based on the visible mass alone. Without the additional gravitational pull from an enormous halo of invisible matter, those outer stars would fly off into intergalactic space. Dark matter provides the missing gravity. It forms a spherical halo that extends far beyond the luminous disk, encompassing the entire galaxy in an invisible gravitational cocoon. Estimates place the total mass of the Milky Way at roughly 1.5 trillion solar masses, with the vast majority of that mass residing in the dark matter halo rather than in stars or gas. The bright, beautiful galaxy you see in photographs is the visible frosting on an invisible cake that outweighs it by a factor of 10. This means that when astronomers talk about the size of the Milky Way, the answer depends on what you are measuring. The luminous disk spans roughly 100,000 light-years. The known stellar halo extends past 200,000 light-years. The dark matter halo may reach 300,000 light-years or more. The gravitational sphere of influence, the region within which objects remain bound to the galaxy, extends to perhaps 500,000 or even 1 million light-years depending on the model used. If you include the full dark matter halo, the Milky Way is not a flat disk at all. It is a vast, roughly spherical structure with a thin, bright disk embedded in its center, and its true radius dwarfs the visible portion that fills astronomy posters. Recent discoveries have reinforced this expanded picture. The Gaia Space Observatory, launched by the European Space Agency in 2013, has measured the precise positions and motions of nearly 2 billion stars in the Milky Way. This unprecedented dataset revealed previously unknown stellar streams, mapped the three-dimensional structure of the spiral arms with new clarity, and confirmed that the galaxy's disk is warped, bending upward on one side and downward on the other like a record that has been left in the sun. The warp may result from gravitational interactions with the Large Magellanic Cloud, a satellite galaxy that orbits the Milky Way at a distance of approximately 160,000 light-years. Even at that distance, the Large Magellanic Cloud's gravitational tug is strong enough to distort the shape of the galactic disk, demonstrating that the Milky Way does not exist in isolation, but is constantly being influenced by its gravitational neighbours. The Large and Small Magellanic Clouds are the two most prominent satellite galaxies, visible to the naked eye from the southern hemisphere as hazy patches of light. But the Milky Way possesses at least 60 known satellite galaxies, with new faint ones still being discovered in deep surveys. Most are tiny dwarf galaxies containing only a few million stars, but their orbits reveal the total gravitational mass they are responding to. Tracking these satellites and the streams they leave behind has become one of the most powerful methods for measuring the Milky Way's total mass and extent. Every new satellite discovered pushes the known boundary of the galaxy's gravitational reach a little farther outward. The Milky Way is also a cannibal. It grows by consuming smaller galaxies that wander too close. The Sagittarius dwarf elliptical galaxy is currently in the process of being devoured. It has already been stretched into a long stream of stars wrapping around the galactic halo, and within a few 100 million years it will lose its identity entirely, its stars absorbed into the Milky Way's population. This is not a rare event. Forensic analysis of the Milky Way's stellar populations using chemical signatures and orbital data has revealed evidence of multiple past mergers. The most significant known event is the Gaia-Enceladus merger, which occurred roughly 10 billion years ago, when a galaxy approximately 1/4 the Milky Way's mass collided and merged with us. The remnants of that ancient galaxy are detectable today as a distinct population of stars in the halo, with different chemical compositions and orbital characteristics than stars born natively in the Milky Way. Our galaxy was built through billions of years of gravitational accumulation and violent consumption of smaller systems. All of this, the 400 billion stars, the spiral arms, the central black hole, the stellar streams, the dark matter halo, the satellite galaxies being digested, the ancient remnants of past mergers, constitutes a single galaxy, one structure among an estimated 2 trillion in the observable universe. Every fact you just absorbed about the Milky Way, every distance, every mass, every time scale, applies with similar or greater magnitude to each of those 2 trillion other galaxies. Some are smaller than ours, many are comparable, a significant number are far larger, containing 1 trillion or more stars and harbouring supermassive black holes billions of times the mass of our Sun. The nearest major galaxy comparable to the Milky Way is Andromeda, sitting approximately 2.5 million light-years away. That distance deserves its own moment of reckoning. Light leaving Andromeda tonight began its journey 2.5 million years ago, when the ancestors of modern humans were just beginning to use stone tools on the plains of Africa. Every photon from Andromeda that enters your eye carries information that old. You are not seeing Andromeda as it exists now. You are seeing a ghost, an image preserved in ancient light, a portrait of a galaxy as it appeared before your species existed. 2.5 million light-years is the distance to our nearest large neighbour, and it is roughly 10 times the diameter of the Milky Way itself. The space between our galaxy and Andromeda is a gulf so immense that the entire Milky Way, all 200,000 light-years of gravitational territory, all 400 billion stars, all 1.5 trillion solar masses of matter, visible and invisible, could be placed in that gap 12 times over with room to spare. That gap is mostly empty. A few faint dwarf galaxies drift through it. Wisps of intergalactic gas occupy the space at densities even lower than the interstellar medium. Temperatures in this intergalactic void hover near the cosmic background level, just a few degrees above absolute zero. This is the true wilderness of the cosmos, not the space between planets, not the space between stars, but the space between galaxies. A void so deep and so empty that light needs millions of years to cross it at the fastest speed the universe allows. And yet, Andromeda is practically next door. It belongs to the same small gravitational family as the Milky Way, a collection called the Local Group. Beyond the Local Group, the next comparable cluster of galaxies lies tens of millions of light-years away. Beyond that, hundreds of millions. Beyond that, billions. Each step outward multiplies the distance by factors so large that the previous scale vanishes into irrelevance. The Milky Way, this colossal structure that took the entire second part of our journey to describe, a galaxy so vast that light needs 200,000 years to cross it, so massive that trillions of solar masses of matter hold it together, so old that its most ancient stars formed when the universe was barely 1 billion years into its existence. This galaxy is about to shrink to a single luminous dot in the next frame of the cosmic picture. Everything we have discussed so far, the solar system, the interstellar void, the spiral arms, the galactic halo, collapses into one point of light among billions. The next scale up makes the Milky Way look the way Earth looked from the edge of the solar system. Small, getting smaller, and nowhere near the end. Andromeda is falling toward us, not drifting, not wandering, falling. The Milky Way and Andromeda are locked in a mutual gravitational embrace that has been pulling them together for billions of years. Andromeda approaches at roughly 250,000 miles per hour, closing the 2.5 million light-year gap between us with the patience of cosmic time. In approximately 4 to 5 billion years, the two galaxies will collide. Their spiral arms will distort. Their halos of dark matter will interpenetrate. Hundreds of billions of stars will rearrange themselves over the course of 1 billion years into a single massive elliptical galaxy that astronomers have preemptively named Milkomeda. The collision sounds catastrophic, but individual stars are so widely separated that direct stellar impacts will be extraordinarily rare. The Sun, if it still exists at that point, will likely survive the merger with its planets intact, flung into a new orbit around the combined galactic center. The violence of a galaxy collision is gravitational, not physical. It reshapes structure without smashing the components. But the collision between the Milky Way and Andromeda is a local affair, a private gravitational drama between two neighbors. To understand the true scale of what surrounds us, we need to zoom out far enough that this impending merger between two galaxies containing a combined total of roughly 1 trillion stars becomes a minor event barely worth noting in the larger cosmic picture. The Milky Way and Andromeda are the two dominant members of a gravitational family called the Local Group. This collection includes more than 80 known galaxies spread across a volume roughly 10 million light-years in diameter. Most members are dwarf galaxies, faint, small collections of a few billion or even a few million stars each. The Triangulum galaxy, also called Messier 33, is the third largest member, containing about 40 billion stars and sitting roughly 3 million light-years from the Milky Way. Everything else in the Local Group is substantially smaller. The Large Magellanic Cloud holds perhaps 30 billion stars. The Small Magellanic Cloud, 7 billion. Many of the dwarf satellites contain so few stars that they were not even discovered until deep sky surveys revealed them hiding in the Milky Way's glare. The Local Group is gravitationally bound. Despite the expansion of the universe pushing distant objects apart, the galaxies within the Local Group are close enough and massive enough that their mutual gravity overcomes that expansion. They orbit around a common center of mass located somewhere between the Milky Way and Andromeda, bound together for the foreseeable cosmic future. This gravitational binding is what distinguishes a galaxy group from a random scattering of galaxies that happen to be near each other. The Local Group is a real physical structure, a cosmic household where the members are permanently linked. 10 million light-years across, 80 galaxies. This sounds like a substantial community until you learn what lies just beyond the neighborhood. The Virgo cluster sits approximately 54 million light-years from the Local Group. It contains over 1,300 known galaxies, packed into a volume roughly 15 million light-years across. At its heart sits Messier 87, a giant elliptical galaxy harboring a supermassive black hole with a mass of 6.5 billion solar masses, more than 1,000 times the mass of the black hole at the Milky Way's center. In 2019, the Event Horizon Telescope produced the first direct image of a black hole using Messier 87's monster as the target, capturing the glowing ring of superheated plasma swirling around its shadow. That image traveled 54 million light-years to reach us, meaning the light was emitted when the earliest ancestors of modern horses were beginning to appear on Earth. The Virgo cluster is not just larger than the Local Group. It is a fundamentally different category of structure. Galaxy clusters are the most massive gravitationally bound objects in the universe. They contain not only hundreds or thousands of individual galaxies, but also vast quantities of superheated gas called the intracluster medium. This gas, heated to tens of millions of degrees by the gravitational energy of the cluster's formation, glows in X-ray wavelengths and actually contains more mass than all the stars in all the cluster's galaxies combined. The visible galaxies are islands floating in an ocean of invisible hot plasma, and surrounding everything, outweighing everything else by a factor of roughly 5 to 1, sits the cluster's dark matter halo. When astronomers add up the total mass of the Virgo cluster, including galaxies, hot gas, and dark matter, the figure reaches approximately 1.2 quadrillion solar masses. That is 1.2 times 10 to the 15th power suns, a number that has stopped meaning anything to the human brain. The local group itself is falling toward the Virgo cluster. Our entire galactic neighborhood, all 80-plus galaxies, is being pulled toward Virgo at roughly 400 kilometers per second. We will never reach it. The expansion of the universe is carrying the Virgo cluster away from us slightly faster than we are falling toward it. So the gap between us and Virgo is slowly growing despite our motion in its direction. But the gravitational influence of the Virgo cluster is real and measurable. It distorts the motions of every galaxy in our region of space, adding a systematic velocity component that astronomers must carefully subtract when measuring cosmic expansion rates. But before we leave the immediate neighborhood of the local group, pause at the gulf that separates us from the Virgo cluster. 54 million light-years of intergalactic space. This is not merely the interstellar void writ large. It is a qualitatively different kind of emptiness, and it deserves its own reckoning. Between galaxies, the density of matter drops to levels that make interstellar space seem crowded by comparison. The intergalactic medium in the voids between galaxy groups contains roughly 1 to 10 atoms per cubic meter. Not per cubic centimeter, per cubic meter. The air in the room where you are sitting contains approximately 25 trillion molecules per cubic meter. The interstellar medium within the Milky Way holds about 1 million atoms per cubic meter. Intergalactic space is 1 million times emptier than that. If you could somehow teleport to a random point in the gulf between the local group and the Virgo cluster, you would float in a vacuum more perfect than anything any laboratory on Earth has ever achieved or likely ever will achieve. The temperature would hover just above the cosmic microwave background temperature of 2.7 degrees Kelvin, barely above absolute zero. No star would be close enough to warm you. No galaxy would be close enough to see with the naked eye except as the faintest imaginable smudge. The darkness would be absolute, the silence total, the isolation complete. This emptiness is not merely a gap between interesting objects. It is the dominant physical reality of the universe. If you placed a pin randomly on a map of the cosmos, the overwhelming probability is that it would land in intergalactic space, not inside a galaxy. Most of the universe is void. Galaxies are the exceptions, rare condensations of matter floating in an ocean of almost nothing. We live in one of those exceptions, which gives us a deeply misleading impression of how full the universe is. The night sky, even at its emptiest, teems with light compared to the true average condition of the cosmos. Now consider what it means to cross that void. Light, the fastest thing in the universe, needs 54 million years to travel from the Virgo cluster to the local group. When that light departed, the Indian subcontinent was still crashing into Asia, slowly pushing up the early Himalayas. Whales had just begun evolving from land-dwelling ancestors. The entire history of the human lineage, every hominin species, every stone tool, every written word, every war, every symphony, every scientific theory, fits within a period shorter than 1% of that light travel time. The intergalactic gulf is not measured in human time. It is measured in evolutionary time, in geological time, in spans so vast that entire branches of life's tree grow, flourish, and go extinct, while a single photon crosses from one galaxy cluster to another. The Virgo cluster itself deserves a longer look, because galaxy clusters are not just collections of galaxies. They are the most massive gravitationally bound objects in the universe, and they operate as physical systems with their own internal dynamics, their own weather, and their own dark matter architecture. A galaxy cluster is held together by gravity, but the gravitational well is overwhelmingly dominated by dark matter. In a typical cluster, dark matter accounts for roughly 80% of the total mass. The hot intracluster gas contributes about 15%. The galaxies themselves, the brilliant objects that give the cluster its visual identity, account for a mere 5%. The galaxies are decoration. The dark matter is the structure. This ratio has been confirmed repeatedly through multiple independent methods, and it presents one of the most compelling cases for the existence of dark matter anywhere in observational cosmology. Gravitational lensing provides the most visually dramatic evidence. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends the light, distorting and magnifying the background galaxy's image. In some cases, the distortion produces arcs, rings, or multiple images of the same background galaxy arranged symmetrically around the cluster. The amount of distortion reveals the total mass responsible for the bending. When astronomers calculate the mass required to produce the observed lensing effects, they consistently find far more mass than the visible galaxies and hot gas can account for. The missing mass is dark matter. The Bullet cluster, located roughly 3.8 billion light-years from Earth, provides what many physicists consider the single most convincing direct evidence for dark matter. This system consists of two galaxy clusters that collided at roughly 10 million miles per hour. During the collision, the hot gas from each cluster, which interacts electromagnetically, slammed together and slowed down, piling up between the two clusters. This gas is visible in X-ray observations as a bright concentration between the clusters. But gravitational lensing maps reveal that the majority of the mass in each cluster passed straight through the collision without slowing down at all. The dark matter components of the two clusters, which interact only through gravity, sailed through each other like ghosts. The result is a system where the visible mass and the gravitational mass are spatially separated. The gas is in the middle. The dark matter is on the outsides. This separation is essentially impossible to explain without invoking a form of matter that does not interact with ordinary matter except through gravity. The Bullet cluster is dark matter's fingerprint, caught in the act. The hot gas that fills galaxy clusters is itself a remarkable substance. It reaches temperatures of 100 million degrees, far hotter than the cores of most stars. At these temperatures, atoms are fully ionized, stripped of all their electrons, forming a plasma that glows intensely in X-ray wavelengths. This intracluster medium is not a minor component. It contains more baryonic mass, meaning ordinary matter made of protons and neutrons, than all the stars in all the cluster's galaxies combined. The galaxies contribute most of the light, the gas contributes most of the normal matter. Neither one dominates the gravitational budget. That belongs to dark matter. X-ray observatories like Chandra and XMM Newton have mapped the distribution of this hot gas in dozens of galaxy clusters, revealing complex structures including shock fronts, where infalling material collides with the existing medium, cold fronts, where dense gas cores slosh back and forth within the cluster potential, and cavities blown by jets from supermassive black holes at the centers of the largest cluster galaxies. These central galaxies, called brightest cluster galaxies, are the most massive galaxies in the universe, containing up to several trillion stars and harboring supermassive black holes with masses reaching tens of billions of solar masses. The jets from these black holes can extend hundreds of thousands of light years into the surrounding medium, pumping enormous quantities of energy into the intracluster gas and preventing it from cooling and collapsing to form new stars. This feedback loop between black hole activity and cluster gas dynamics is one of the most active areas of research in modern astrophysics. Zoom out further. The local group and the Virgo cluster are both embedded within a vastly larger structure called the Laniakea supercluster, identified and named in 2014 by a team led by astronomer Brent Tully. Laniakea spans roughly 500 million light-years and contains the mass of approximately 100 million billion suns distributed across an estimated 100,000 galaxies. The name comes from Hawaiian and means immeasurable heaven, which turns out to be only a slight exaggeration. Laniakea was mapped not by counting galaxies but by tracking their motions. Every galaxy in the universe has a peculiar velocity, a motion through space driven by the gravitational pull of nearby mass concentrations. By measuring the peculiar velocities of thousands of galaxies, Tully's team identified coherent flow patterns where galaxies across enormous volumes of space were all streaming in the same general direction. Laniakea is defined as the volume of space within which all galaxy motions converge toward a single gravitational focal point called the Great Attractor. This massive concentration of matter, partially hidden behind the dense dust of the Milky Way's galactic plane, pulls everything within Laniakea toward it with a gravitational force that influences galaxy motions across hundreds of millions of light years. The Milky Way, the Local Group, the Virgo Cluster, and tens of thousands of other galaxies and clusters are all falling toward the Great Attractor as part of a single immense gravitational drainage basin, 500 million light-years. The number sits on the page, inert and abstract. To feel what it means, consider that light travelling from one edge of Laniakea to the other would need 500 million years to make the journey. When that light departed, the most complex life on Earth consisted of simple marine organisms. Fish had not yet evolved. The entire Cambrian explosion, the rise of vertebrates, the age of dinosaurs, the evolution of mammals, and the emergence of human civilization would all occur during that single beam of light's transit across one supercluster. And Laniakea is not alone. It borders other superclusters. The Perseus-Pisces supercluster lies adjacent to Laniakea. The Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe, sits roughly 650 million light-years away and exerts its own enormous gravitational pull. Laniakea itself may be falling toward Shapley as part of an even larger flow pattern that astronomers are still working to map. The hierarchy of gravitational structures does not stop at superclusters. It continues upward into the largest patterns of matter distribution the universe contains. This is where the cosmic web reveals itself. If you could somehow step outside the universe and look at the distribution of all matter across billions of light-years, you would not see galaxies scattered randomly through space. You would see a vast interconnected network of filaments, walls, and nodes, resembling the structure of a sponge, or the neural connections in a brain, or the pattern of soap bubbles in a foam. This network is called the cosmic web, and it represents the largest scale organization of matter in existence. The cosmic web consists of 4 types of structures. Nodes are the densest regions, the intersections where multiple filaments converge. Galaxy clusters form at these nodes, anchored by enormous concentrations of dark matter. Filaments are long, thread-like bridges of dark matter and gas stretching between nodes, often spanning hundreds of millions of light-years in length, while maintaining widths of only 10 to 20 million light-years. Walls are vast, sheet-like surfaces where filaments intersect to form broad planar structures containing thousands of galaxies arranged in thin layers. And between all of these structures lie cosmic voids, enormous underdense regions where almost nothing exists. The filaments are the highways of the cosmos. Gas flows along them, funneled by dark matter's gravity toward the nodes where galaxy clusters grow. Galaxies themselves form preferentially along filaments, strung out like beads on a string. The matter in filaments is not exclusively dark. Ordinary hydrogen and helium gas threads through these structures, heated to temperatures of 100,000 to 10 million degrees. This warm, hot intergalactic medium has long been predicted by cosmological simulations, but was extraordinarily difficult to observe because it glows too faintly for most instruments to detect. That changed recently. In early 2025, an international research team using the MUSE instrument on the European Southern Observatory's Very Large Telescope published an unprecedented high-definition image of a cosmic web filament connecting 2 galaxies at a distance. Corresponding to when the universe was roughly 2 billion years old, the filament stretched approximately 3 million light-years, and for the first time, researchers could directly trace the boundary between gas residing inside galaxies and gas contained within the cosmic web itself. When compared to state-of-the-art supercomputer simulations of cosmic structure, the observed filament matched theoretical predictions with remarkable precision. This was the first time the faint glow of intergalactic gas within a filament had been imaged in such detail. confirming a fundamental prediction of modern cosmology. Also in late 2025, a team led by researchers at the University of Oxford identified one of the largest rotating structures ever observed, a razor-thin chain of 14 hydrogen-rich galaxies embedded within a much larger cosmic filament, roughly 50 million light-years long, and located about 140 million light-years from Earth. The galaxies within this thin strand were found to be spinning in the same direction as the filament itself, far more frequently than random chance would predict. This discovery challenged existing models of how galaxies acquire their rotational motion and suggested that the cosmic web may influence galaxy spin more strongly and over larger scales than previously believed. Meanwhile, ESA's Euclid Space Telescope has been assembling the most ambitious map of cosmic structure ever attempted. Launched in July 2023, Euclid released its first batch of survey data in March 2025, covering 63 square degrees of sky and revealing 26 million galaxies in just its initial deep field observations. Within these fields, the large-scale organization of galaxies along the cosmic web was already visible, with clusters connected by filamentary strands of galaxies stretching across billions of light-years of cosmic history. Euclid's mission will ultimately survey a third of the entire sky, measuring the shapes of billions of galaxies over 10 billion years of cosmic time and constructing a three-dimensional map of dark matter distribution on scales never before achieved. The first major cosmology dataset is expected in October 2026. When it arrives, it will provide the most detailed picture ever assembled of how the cosmic web has evolved since the universe was young. The structures revealed by these surveys are staggering. The Sloan Great Wall, discovered through the Sloan Digital Sky Survey, stretches approximately 1.4 billion light-years across, making it one of the largest known coherent structures. It consists of thousands of galaxies arranged in a wall-like formation that extends across a significant fraction of the observable universe. Even larger is the Hercules Corona Borealis Great Wall, detected through the clustering of gamma-ray bursts and estimated to span roughly 10 billion light-years. If confirmed at that scale, it represents a structure so immense that light would need more than 1/10 of the current age of the universe to travel from one end to the other. But the structures are only half the picture. The other half is emptiness. Cosmic voids occupy roughly 80% of the universe's volume. These immense underdense regions, typically spanning 100 to 500 million light-years across, contain almost no galaxies. They are the bubbles in the cosmic foam, the hollow spaces between the filaments and walls where matter has drained away under gravity's patient influence over billions of years. The Bode's Void, discovered in 1981, stretches approximately 330 million light-years in diameter and contains fewer than 60 known galaxies. If the Milky Way sat at the center of the Bode's Void, the nearest large galaxy would be so distant it would appear as a faint smudge, detectable only through powerful telescopes. The night sky would be vastly emptier than what we see from our position in the cosmic web. The emptiness inside voids is not absolute. Dark matter exists there at reduced density, forming tenuous filamentary structures too faint and sparse to gravitationally capture enough ordinary matter for galaxy formation. Dark energy, which appears to maintain constant density regardless of how much space expands, dominates voids completely. With so little matter to resist expansion, voids grow faster than the cosmic average, inflating like balloons and pushing their boundaries outward into the surrounding filaments. This process has been ongoing for billions of years and will continue indefinitely. Voids are getting larger, filaments are getting thinner. The contrast between dense regions and empty regions is increasing over time. The cosmic web is slowly dissolving, its delicate structure being stretched apart by the relentless pressure of dark energy. The origin of all this structure traces back to the first moments after the Big Bang. In the initial fraction of a second, during the epoch of cosmic inflation, quantum fluctuations in the density of the primordial plasma were stretched to macroscopic scales. These fluctuations were extraordinarily tiny, variations of roughly 1 part in 100,000, but they were enough. regions with slightly higher density attracted slightly more matter through gravity. Regions with slightly lower density lost matter to their denser neighbours. Over hundreds of millions of years, this process amplified. Dense regions collapsed into the first stars, which gathered into galaxies, which clustered into groups, which aligned along filaments. Underdense regions emptied further, expanding into voids. The cosmic web is the final product of gravitational amplification, acting on quantum noise for 13.8 billion years. The largest structures in the visible universe grew from the smallest fluctuations physics allows. The cosmic microwave background radiation provides a snapshot of those fluctuations when the universe was just 380,000 years old. Satellites including COBE, WMAP, and Planck mapped tiny temperature variations across the entire sky, revealing the seeds of all future structure. Warmer spots corresponded to slightly denser regions. Cooler spots corresponded to slightly less dense regions. Scientists feed these measured patterns into supercomputer simulations that model how gravity, dark matter, dark energy, and ordinary matter interact over billions of years. The resulting simulated universes produce cosmic webs that match the observed one with impressive fidelity. Filaments form in the simulations at the same scales and densities as real filaments. Voids open up with the same sizes and emptiness. Galaxy clusters emerge at the nodes with comparable masses and temperatures. This agreement between theory and observation is one of the great triumphs of modern cosmology. We understand, in broad strokes, how the cosmic web formed and why it looks the way it does. But the agreement is not perfect. Some observed structures appear larger or more extreme than simulations comfortably produce. The Hercules Corona Borealis Great Wall, if its size is confirmed, pushes the limits of what standard cosmological models predict. Supervoids like the KBC void, estimated at roughly 2 billion light-years in diameter with a density deficit of around 20%, are rare enough in simulations that their existence raises questions about whether our models fully capture the range of cosmic structure. These tensions are not crises, they are frontiers, places where observation pushes theory to evolve and improve. The cosmic web also serves as a laboratory for studying dark energy, the mysterious force driving cosmic acceleration. Because voids expand faster than average, and clusters resist expansion through their concentrated gravity, comparing the growth rates of different cosmic structures at different epochs in cosmic history allows scientists to measure how dark energy's influence has changed over time. The Euclid mission was designed precisely for this purpose. By mapping how the shapes and positions of billions of galaxies have shifted over the past 10 billion years, Euclid will test whether dark energy is a cosmological constant, unchanging and uniform, or whether it varies in strength across space and time. Either answer would be revolutionary. A constant dark energy confirms the simplest theoretical model, but leaves its fundamental nature unexplained. A varying dark energy demands entirely new physics that no current theory fully provides. Consider now the full scope of what the cosmic web represents. You began this journey standing on a planet 8,000 miles wide. You crossed a solar system whose gravitational boundary extends roughly 2 light-years. You traversed interstellar space to appreciate a galaxy 200,000 light-years across. You stepped out to the local group at 10 million light-years, the Virgo cluster at 54 million light-years, the Laniakea supercluster at 500 million light-years. And now the cosmic web stretches before you in every direction. A tapestry of filaments, walls, clusters, and voids, extending for billions of light-years, organized into patterns so large that individual galaxies are less than specks within them. Every galaxy ever photographed by the Hubble Space Telescope, every cluster mapped by X-ray observatories, every supercluster identified through galaxy surveys, exists as a minor feature within this web. The Milky Way, the structure whose size consumed an entire section of this story, is a single node in a single filament within a single supercluster within a web that extends to the limits of what we can observe. The Virgo cluster, with its 1,300 galaxies and quadrillion solar masses, is one node among millions. Laniakea, with its 100,000 galaxies, is one drainage basin among countless others. To appreciate what has just happened in this journey, consider the following chain of containment, each link of which would have been incomprehensible to the occupants of the previous one. Earth is one planet orbiting one star. That star is one among 400 billion in a galaxy. That galaxy is one of more than 80 in the local group. The local group is one small structure falling toward the Virgo cluster. The Virgo cluster is one node among many in the Laniakea supercluster. Laniakea is one supercluster among millions in the observable cosmic web. Each structure contains the previous one the way an ocean contains a single drop of water, and at every step the transition from one scale to the next rendered the previous scale invisible. Here is a way to feel the compression. If you represented the entire observable universe as a sphere the size of Earth, the Laniakea supercluster would be the size of a mid-sized city inside it, roughly 70 kilometers across. The Virgo cluster would shrink to a couple of kilometers, a short walk through a single neighborhood. The local group would compress to a little over a kilometer, barely a few city blocks. The Milky Way would be the length of a swimming pool. And the solar system, everything humanity has physically explored, every spacecraft we have ever launched, every signal we have ever sent, would be smaller than a single bacterium. A bacterium inside a swimming pool, inside a neighborhood, inside a city, inside the Earth. That is the compression. Each level does not merely reduce the previous one, it annihilates it. The cosmic web achieves something no smaller structure can. It reveals the universe's blueprint. The pattern of filaments, walls, and voids is not random. It is the direct, inevitable consequence of gravity, acting on the initial density fluctuations from the Big Bang across 13.8 billion years of cosmic evolution. Every thread of the web traces a line of slightly higher primordial density. Every void marks a region that started with slightly less matter than its surroundings. The cosmic web is a fossil record of the quantum fluctuations that occurred during cosmic inflation, magnified from subatomic scales to structures spanning billions of light years. It is the universe's autobiography, written in the language of gravity and time. The web is also a clock. Because light travels at a finite speed, observing cosmic structure at different distances means observing it at different ages. Nearby filaments and clusters show the web as it exists today. Distant ones show how it looked billions of years ago. By comparing the web's structure at different epochs, astronomers can watch cosmic evolution in action. The filaments were denser in the past. The voids were smaller. Clusters were less massive. The web was tighter, more compact, less defined. Watching the web evolve over cosmic time is like watching a time-lapse of frost crystals forming on a window, except the window is billions of light years across, and the frost took 10 billion years to grow. The DESI instrument, the Dark Energy Spectroscopic Instrument, is currently conducting the most ambitious three-dimensional map of the cosmic web ever attempted, measuring precise distances to tens of millions of galaxies and quasars. Its early results, released in stages beginning in 2024, have already produced the most detailed picture of how cosmic expansion has evolved over the past 11 billion years. Combined with Euclid's wide-field imaging and the James Webb Space Telescope's deep spectroscopy, these surveys are converging on a comprehensive understanding of how the cosmic web grew from primordial seeds into the vast structure we observe today. Every new survey reveals the same humbling truth. The structures we can see are immense beyond comprehension, and they are contained within a volume that may be an infinitesimal fraction of the whole. And the cosmic web itself is contained within something. A boundary, not a wall or an edge, but a horizon imposed by the speed of light and the age of the universe. Everything we have discussed so far, from your footsteps to filaments spanning billions of light years, exists inside a finite volume of space defined by how far light has traveled since the universe began. Beyond that boundary lies more universe, potentially infinitely more, that we have never seen and may never see. The cosmic web, in all its staggering immensity, is about to fit inside a single sphere, and that sphere may turn out to be an atom-sized fraction of what actually exists. The observable universe has a diameter of approximately 93 billion light-years. That sentence contains one of the most commonly misunderstood numbers in all of science, so it deserves careful unpacking before we go any further. The universe is 13.8 billion years old. Light has been travelling since the cosmos became transparent to radiation roughly 380,000 years after the Big Bang. You might reasonably expect, then, that the farthest thing we could possibly see is 13.8 billion light-years away. But the universe has been expanding throughout that entire time. Objects that emitted light 13.8 billion years ago were much closer to us when that light began its journey. During the billions of years that light has been travelling toward Earth, the expansion of space has been carrying those objects farther and farther away. By the time their ancient photons finally reach our telescopes, the objects themselves have been swept outward to a current distance of approximately 46.5 billion light-years. Double that to account for the opposite direction, and you get the full diameter. 93 billion light-years. The observable universe is vastly larger than the age of the universe naively implies, because space itself has been stretching while the light was in transit. This observable sphere is centered on Earth, not because Earth is special, but because the observable universe is defined by the observer's location. Every point in the cosmos has its own observable sphere, centered on itself, extending 46.5 billion light-years in every direction. An astronomer on a planet in the Andromeda galaxy would have a slightly different observable volume, overlapping with ours in most places, but extending 2.5 million light-years farther in one direction and falling 2.5 million light-years short in the opposite direction. Every observer sits at the center of their own visible cosmos. This is not a privilege. It is a geometric inevitability of finite light speed in an expanding universe. Within this sphere, current estimates place the total number of galaxies at roughly 2 trillion. That figure, published by a team using Hubble Space Telescope data combined with mathematical modelling, accounts for the many small, faint galaxies that fall below the detection threshold of even our most powerful instruments. Each of those 2 trillion galaxies contains anywhere from a few million to several trillion stars. Summing across the entire observable volume produces a total stellar population on the order of 10 to the 24th power. That is 1 septillion stars. Written out, the number is a 1, followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach, in every desert, on every seafloor, across the entire surface of the Earth. And the pace of discovery continues to accelerate. In January 2026, astronomers confirmed that a galaxy designated MOM Z14, discovered using the James Webb Space Telescope, is the most distant galaxy ever spectroscopically verified. Its light reveals the universe as it appeared just 280 million years after the Big Bang, corresponding to a redshift of 14.44. The galaxy is currently located approximately 33.8 billion light-years from Earth due to cosmic expansion during the intervening eons. MOM Z14 is brighter, more compact, and more chemically enriched than theoretical models predicted for galaxies forming so soon after the origin of the universe. Its existence, along with roughly 100 times more luminous early galaxies than standard cosmology anticipated, suggests that star formation in the infant universe was far more vigorous and efficient than scientists expected. The JWST has not just pushed back our observational frontier, it has revealed that the early universe was assembling complex structures with a speed that challenges the models we built to explain it. The farthest boundary of our observable volume is not marked by distant galaxies, it is marked by a wall of light. The cosmic microwave background radiation is the oldest electromagnetic signal in existence. Released when the universe was approximately 380,000 years old and had cooled enough for the first stable atoms to form. Before that moment, the universe was an opaque fog of plasma so hot and dense that photons could not travel more than microscopic distances without scattering off free electrons. When atoms formed and the electrons were captured into orbits, the fog cleared. Light was suddenly free to travel, and it has been streaming through space ever since. That primordial light now arrives at Earth from every direction. Stretched by 13.8 billion years of cosmic expansion into microwave wavelengths, with a temperature of approximately 2.725 degrees above absolute zero, it is extraordinarily uniform. In every direction astronomers look, the temperature is the same to within a few hundred thousandths of a degree. This uniformity tells us that the early universe was almost perfectly smooth, with only the faintest ripples of density variation seeded by quantum fluctuations during inflation. Those ripples, mapped in exquisite detail by the Planck satellite, encode the initial conditions from which all cosmic structure eventually grew. Every galaxy, every cluster, every filament of the cosmic web traces its ancestry to the pattern of infinitesimal temperature variations in the cosmic microwave background. The cosmic microwave background also sets an absolute observational limit. No electromagnetic telescope can see beyond it. Before the universe became transparent, no light was free to travel, so no images of earlier epochs can ever be captured using photons. The first 380,000 years of cosmic history are hidden behind this wall of ancient radiation. Other observational windows may eventually pierce this barrier. Gravitational waves generated during inflation could carry information from even earlier moments. Neutrinos decoupled from matter about 1 second after the Big Bang, far earlier than photons, and a cosmic neutrino background should exist, though detecting it remains beyond current technological capability. But for now, the cosmic microwave background is our deepest look into the past, a baby portrait of a universe barely emerged from its primordial state. Beyond the observable universe lies more universe. How much more is a question that current physics can constrain but cannot definitively answer. The most rigorous approach uses measurements of the spatial curvature of the cosmos. If the universe is curved, like the surface of an enormous sphere, then very distant triangles drawn in space would have angles that sum to slightly more or slightly less than 180 degrees, depending on whether the curvature is positive or negative. Measurements from the Planck satellite show that space is flat to within the precision of our instruments. This flatness implies that the universe is either infinite or vastly larger than the observable portion. Statistical analyses based on Planck data suggest that the total universe is at least 250 times larger in radius than the observable volume, corresponding to a minimum diameter of roughly 23 trillion light-years. If that lower bound is correct, the observable universe occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy we can see, at least 15 million more exist beyond our horizon, and that is the conservative estimate. The true universe could be substantially larger, possibly infinite. This possibility demands a moment of sober reflection. If the universe is infinite, it contains an infinite number of galaxies, an infinite number of stars, and an infinite number of planets. In an infinite cosmos where physical laws and constants are uniform, every configuration of matter that is physically possible must occur somewhere. This includes configurations identical to our own solar system, our own planet, and our own civilization. In a truly infinite universe, there must be regions of space where the arrangement of atoms mirrors the exact conditions that form you at this very moment. The implications of infinity are not just strange. They are vertigo-inducing. They challenge the very concept of uniqueness. If everything that can happen does happen somewhere in infinite space, then nothing is truly one of a kind, including you. Whether the universe is infinite or merely unimaginably vast, the portion beyond our observable horizon is permanently inaccessible. This is not a limitation of technology. It is a limitation imposed by the laws of physics. The universe is expanding, and that expansion is accelerating. In 1998, 2 independent teams studying distant Type Ia supernovae discovered that the expansion of the universe is not slowing down under the braking influence of gravity, as most physicists expected. It is speeding up. Something is pushing space apart with increasing vigor. That something, labeled dark energy for lack of a better understanding, constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the atoms and molecules that build stars and planets and people, accounts for roughly 5%. The universe is overwhelmingly composed of substances we can detect only through their gravitational effects, and whose fundamental nature remains one of the deepest unsolved problems in physics. Dark energy's accelerating push has a consequence that plays out across cosmic time with quiet but devastating finality. Galaxies beyond a certain distance are currently receding from us faster than the speed of light. This does not violate Einstein's relativity because the galaxies are not moving through space faster than light. Space itself is expanding, carrying them along, but the practical result is identical. Light emitted by those galaxies today will never reach us. They are beyond our causal horizon. We can neither observe them, communicate with them, nor be influenced by them in any way. And the number of galaxies crossing this threshold grows with every passing moment. The accelerating expansion is gradually shrinking the pool of cosmic neighbors with which we can ever have any physical interaction. In approximately 100 billion years, if dark energy continues behaving as current measurements indicate, every galaxy beyond the local group will have receded beyond the cosmic event horizon and redshifted into invisibility. A civilization arising in that far future epoch would look out into the sky and see only the merged remnant of the Milky Way and Andromeda, a single giant elliptical galaxy surrounded by a handful of gravitationally bound satellites. Within 1 trillion years beyond that, even the cosmic microwave background would have stretched to wavelengths too long for any conceivable instrument to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies would have vanished. Those future astronomers, no matter how brilliant, would have no observational basis for concluding that a larger universe existed. They would live in a cosmic dark age, isolated in a single galaxy, with the true nature of the cosmos permanently hidden from them by the expansion of space itself. We happen to exist during a brief window in cosmic history, when the evidence is still visible. The cosmic microwave background still glows faintly in our instruments. Distant galaxies still send photons that arrive at our detectors after journeys of billions of years. The large-scale structure of the cosmos is still imprinted in galaxy surveys and gravitational lensing maps. We can still piece together the story. This window will not last, not on cosmic timescales. The universe is slowly erasing its own history, pulling the evidence beyond reach one galaxy at a time. Now stand back and consider the full journey. You started this story as a 6-foot-tall figure on the surface of a planet 8,000 miles across. That planet orbits a star 93 million miles away. That star is one among 400 billion in a galaxy 200,000 light-years wide. That galaxy is one of more than 80 in a local group, 10 million light-years across. That group belongs to a cluster of over 1,000 galaxies 54 million light-years away. That cluster exists within a supercluster 500 million light-years in extent. That supercluster is threaded into a cosmic web of filaments and voids spanning billions of light-years. And all of it, every filament, every void, every galaxy, every star, every planet, every atom, exists inside an observable sphere, 93 billion light-years in diameter, that may represent less than 1/15 millionth of the total universe. Each of those steps followed the same pattern. A scale that seemed unfathomably large was revealed to be negligibly small inside the next one. The solar system, which took decades for our fastest spacecraft to partially traverse, vanished to a point within the galaxy. The galaxy, with its hundreds of billions of stars and trillions of solar masses, became a single luminous dot within the local group. The local group dissolved into a minor feature of the Virgo cluster. The Virgo cluster shrank to one node among millions in the cosmic web. And the cosmic web, the largest structure we can map, fits inside an observable volume that may itself be an atom-sized fraction of the whole. This is the central truth about cosmic scale, and it is more radical than simply saying the universe is big. The universe is recursively humbling. Every frame of reference you adopt, no matter how vast, turns out to be a tiny detail inside a larger frame you have not yet considered. There is no scale at which you can stop and say, now I have reached the level that matters. Every level is simultaneously enormous from below and insignificant from above. The solar system is vast beyond human experience and irrelevant on galactic scales. The galaxy is colossal beyond galactic experience and invisible on cosmic scales. The observable universe is the largest thing we can measure, and it may be an infinitesimal sliver of what exists. This recursion is what makes the true scale of the universe different from mere bigness. A large number is just a large number. You can read it, note it, and move on. But the systematic collapse of every scale into the next one produces something more unsettling. It reveals that human intuition is not just slightly miscalibrated for the cosmos. It is fundamentally, structurally, irreparably inadequate. Our brains evolved to navigate a world of footsteps and throwing distances. We can stretch our intuition to encompass continents and oceans with some effort. Beyond that, numbers become abstractions. The distance to the moon is a number. The diameter of the galaxy is a number. The size of the observable universe is a number. But none of these numbers connect to any physical sensation your brain can generate. You cannot feel the emptiness between galaxies. You cannot sense the curvature of cosmic filaments. You cannot intuit the 14 billion year journey of a photon from the cosmic microwave background. The numbers exist in your mind as pure data, unanchored to experience, ungrounded in anything your body has ever encountered. And yet, here you are, a temporary arrangement of atoms on the surface of a small planet orbiting an ordinary star in the suburbs of one galaxy among 2 trillion. Your body is built from elements forged inside stars that exploded before the solar system existed. Every atom in your body heavier than hydrogen was manufactured inside a star that no longer exists. Those atoms were expelled into space through explosions and stellar winds, drifted through interstellar clouds for millions of years, and were eventually swept up by gravity into the collapsing disk of gas that became our solar system. You did not merely come from the universe. You are the universe, rearranged into a pattern that became capable of contemplating itself. Matter that has become aware of matter. Complexity that emerged from simplicity across billions of years of cosmic time. This is not a sentimental observation, it is a physical one. The same laws of physics that govern the expansion of cosmic voids and the collapse of galaxy clusters also govern the electrochemical signals firing in your neurons as you process these words. Gravity shaped the cosmic web. Nuclear fusion built the elements, chemistry assembled the molecules, biology organized the cells, and consciousness emerged from that biological complexity, a phenomenon so improbable that we have found evidence of it in exactly one location in the entire observable universe, and yet so powerful that it can reconstruct the history of that universe from fragments of ancient light. A species that evolved 70,000 generations ago on a patch of African grassland has built instruments capable of detecting photons from 13.5 billion years in the past. It has mapped the distribution of invisible matter across billions of light years. It has photographed the shadow of a black hole in another galaxy. It has measured the faint glow of the primordial fireball that filled the universe before any star existed. It has landed machines on other worlds, detected gravitational waves from colliding neutron stars, and confirmed that the expansion of the cosmos is accelerating under the influence of a force it does not yet understand. That last fact bears repeating. We do not understand 68% of the energy in the universe. We cannot directly detect 85% of the matter. We cannot observe more than a small fraction of the total cosmic volume. Our most successful theory of particle physics is incomplete. Our best model of cosmic evolution contains parameters we measure, but cannot derive from first principles. We are, by any honest accounting, profoundly ignorant about the fundamental nature of the reality we inhabit. But we know more today than we did yesterday. The Euclid telescope is building the largest three-dimensional map of cosmic structure ever assembled. The James Webb Space Telescope is pushing the observational frontier toward the era of the very first stars. The dark energy spectroscopic instrument is measuring the expansion history of the universe with unprecedented precision. Gravitational wave observatories are opening entirely new channels of cosmic observation. Each of these instruments will refine our understanding, correct our errors, and reveal new layers of structure and complexity that we have not yet imagined. The true scale of the universe does not diminish human significance in the way people often assume. The common reaction to cosmic scale is a sense of futility. We are small, therefore we do not matter. But that conclusion does not follow from the evidence. Smallness is a spatial measurement. Significance is not. A single human allele carrying a mutation that alters the course of evolution is microscopically small and biologically momentous. A single equation written on a chalkboard can redirect the technological trajectory of a civilization. The relationship between physical size and cosmic importance is not the linear one our intuitions suggest. The universe does not award significance based on volume. What the true scale of the universe actually reveals is something more nuanced and more extraordinary. It reveals that the cosmos is structured in a way that permits, across billions of years and billions of light years, the emergence of organized complexity from initial simplicity. Quantum fluctuations became cosmic structure. Hydrogen became stars. Stars became heavy elements. Heavy elements became rocky worlds. Chemistry became biology. Biology became minds capable of reconstructing this entire chain of events from observations made on the surface of one small planet. The scale of the universe is not a statement about human irrelevance. It is a statement about the depth and richness of the physical processes that produced us. The journey from quantum noise to conscious observation required every one of those billions of light years, and every one of those billions of years. The vastness is not incidental. It is the mechanism. You are sitting on a rock 8,000 miles wide, orbiting a star that is one of 400 billion, inside a galaxy that is one of 2 trillion, within an observable volume that may be 1/15,000,000th of the whole. Every scale you thought was the biggest turned out to be a rounding error inside the next one. The numbers are real. The distances are physical. And none of it, not a single light year, is wasted. Because somewhere in that incomprehensible expanse of space and time, the universe did something that no amount of emptiness can diminish. It woke up, looked around, and began to measure itself.